Okay, lecture 14, robot motion control. Let's first define what do we mean by robot motion control problems. And there's other control problems, like, for example, force control. You just control not about, you don't care about where the robot are, you care about how much force it applied to the environment. Okay, that's force control, or that's hybrid motion and force control. But all of these, the foundation is really motion control. And the foundation for motion control is relatively simple. It's just linear control plus some optimization. If you learn this stuff 5 years or maybe 10 years ago, there will be a lot of details. But nowadays, I think everything can be unified. At least I tend to think this way. I hope you can also get that. Okay, so before that, let's set up stage for defining motion control problems. We derived, in the first half of this class, we derived the robotic dynamics model, right? This is our torque. Suppose we have n joints, that's our torque vector. And this is a typo. I will use Q. I switched my notation to be more consistent with the literature that talks about this topic. I hope you can change that as well. Now, let's think about joint variable using Q to represent the joint variable. Okay, it's also called generalized coordinate. This part is the gravity term, and if you have a, let's say this is my arm, right? This is arm. So suppose I have an external force. How should I modify this this equation? If I have an external force, how should I modify this? Plus J transpose Q times F external, okay? If I need, I can do this. And you should be able to derive it. The recursive Newton-Euler algorithm, actually, you just need to understand that algorithm. You know how exactly its part, it's part of the body, whatever the force you need you need to apply or experience from the environment, you know exactly how that affects the joint torque, okay? So that describes the robot dynamics, okay? And suppose we care about some output variable that depends on the robot configuration or robot joint variable. And it can be the end effector frame, entire poles, or can be just the joint, or can be arbitrary function of the joint variable. This is something we need to control. All right. This can be, output, let's say, can be any kind of function of your joint variable. An example could be the entire T in SE3, the end effector frame, right? Or just a particular, let's say the origin of the end effector frame is central. Okay, let's not distinguish that. Let's just use Y to define the quantity that we want to control. And robot control, motion control problem is let Y to track a given reference. Okay, so that's exactly the motion control problems. If I draw a little diagram, that's my robot. Okay, that's an input to the robot. And this is my output of my robot that I care about. If we only care about the end effector origin, then Y will be the origin. If you just care about a particular joint, let's say joint 5 position, then just the joint 5. It's really up to your particular application. And the motion controller, let's call that in general, the motion controller provides or determines the control action that need to be sent to the robot, okay? And the input of the motion controller, well, there can be variations, of course. This is not the unique way to think about this. This is D, okay? Given desired motion that they want to achieve, a motion controller tells you, okay, what kind of control input I need to apply to the robot to achieve that. And how to define this YD that typically we call planar motion planning algorithms. Plan the desired trajectory, then the desired trajectory will be tracked by the motion controller. Okay? And this is my feedback to this. Of course, this guy will also, sometimes the plan need to be updated as well. And so YD will be changed dynamically as well. Okay. There's a lot of details out there, but I will ask you to think about it, or maybe advise or suggest you to think about this in terms of if you have questions. Do you have questions? Uh-huh. 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 Three. Depending on applications, very fast. Motion controller typically. Yeah, very fast. Okay. These loop are different. Yeah, that's a good point. If you have another loop, and the inner part is pretty fast, typically faster than the outer loop. Okay. I would like to think about, there's different methods. There's a lot of different methods. I want to think about them or categorize them in terms of the definitions of U and Y. U is your interface as a motion controller, your interface with the robot. Okay, Y is something you care about. Okay, depending on U and Y, the different cases, then you will have different controller, of course, but all of them follow the exactly, well, hopefully I think you can think of them following exactly the same design principle. And the design principle is I want to emphasize. I'm not going to emphasize the details. I'm going to emphasize the principle. The principle you have to know, all right? So let's talk a little about the categorization of different motion control problems. First of all, I don't think I enumerate all the possible cases, but these are really important ones. The first one is Y could be joint space control, in the sense that my Y is just my joint variable. In other words, I want my joint variable to track a given joint reference. Okay, so I will say oftentimes, this QD, the desired joint reference, is given by the planar. Okay, whoever determines this Y, a QD, we call that planar for now. Okay, and also kind of represented by most of the time polynomials. Okay, you have a desired polynomial of certain order, and the reason is that in this case, so that QD dot, QD double dot, you can differentiate it, okay? Can be obtained without too much noise, obtained without too much noise. Okay, this is outside this particular lecture. It's really about planning part. Okay, so for motion control, let's think about motion control problems. At least what we care about is really that you give me a YD, in this case, joint YD will be QD, and I want to design controller to track it. Okay, there's also so-called task space control. So desired motion is not specified in the joints. It's just specified with respect to or in terms of end effector pose. For example, I want to move to here. The end effector move to grab this chalk. So I need to go here, and the end effector motion planning is directly planned with respect to or in the task space, my end effector frame here. And whatever joint reference I don't provide, I want the motion controller to figure that out automatically. That's typically called task space control, or more precisely, task space motion control. Okay. So in this case, there's a task space. So you're not given a desired joints level reference. You just give an end effector reference. Okay. It could be this could be in ICE3. Okay. Or it can be any function. Actually, it can be any function of Q or joint variables. Maybe I only care about end effector, the origin of an end effector frame, or a pose. Okay. In this case, YD is not QD, it's really about the pose of an end effector frame. So that distinguishes two classes of problems, joint space control or task space control. That's the output. Then each category will further divide according to your assumption of the control input, which is U, this U variable. That's why you see there's a lot of combinations. I don't want you to be kind of get stuck with all this detailed setup. You should know all of them can be viewed as the same kind of principle. Okay. Now, typical assumptions that you can desire, typically assumptions that's called actuation models. It's velocity source. You can directly control the joint velocity. Is this a good assumption, Liuben? Huh? Depends on the application. Okay, it could be different cases. You can desire directly control the velocity. You can directly control the acceleration level. That's a little bit more direct. Or you can directly control the torque. That's a typical three things or three assumptions you can interface with the robot. Okay. If you think about the robot, okay, this is my U, this is my Y. Okay, it's a really abstraction. It's not means you can directly control the velocity source. Inside this, you tell them the source. Inside this, there may be some internal controller can help you generate desired force to achieve that. Okay, it's really about the interface with your robot system. Some robots allow you to directly control the current or current loop or torque. Some robot does not allow you to do it. Can only allow you to specify velocity, joint velocity, or joint position. Okay, it's really depends on the application and depend on your assumption. That's kind of important. Let me just slowly make sure you understand that part. If you gave me an industrial robot, and oftentimes you can directly only specify the joint position. Okay, maybe not even velocity that easily. All of the robot typically you can tell them, okay, that's the position of each joint, you should move there. That's maybe fine, but you cannot directly control the velocity typically. But in our designing analysis, we don't, I mean, the lowest level is velocity control, that I emphasize. If you don't allow me to do the velocity directly, then I can specify velocity control, assume, then integral to generate the desired position. That's your assumption, right? You need to make sure your assumption adapt to the application scenario. I think that will be clear after see some examples, okay? So we first need to specify or review a little bit about the linear control design, very simple. But why I'm doing that, let me tell you, okay? I would think most motion control, most methods are based on linear, it's a linear control design method plus a so-called, well, if you ask me, I would think about them as a feedback linearization, but I'm not going to discuss that in very kind of a rigorous way. But I mean, in other words, I will try to have a very kind of a simple way to approach it with inner outer loop control. So that's the structure. So the motion control problem, by definition for robotic arm, this is a nonlinear system. If you look at this thing, it's nonlinear. Okay, this is really a nonlinear system. It's not a linear system, but all the examples you see in the literature or in textbook, they will just involve linear control design plus some inner outer loop thing. Okay, so that's why I need to somehow specify or review a little bit about linear control design method. That's almost everything you need to know, even to prove the closed loop behavior of the motion control method. Okay, that's simple. I will be very quick. Make sure we're on the same page. When you design controller, the things you care about is the performance index. Sometimes, well, if you look at step response, you will have this kind of step response, right? And that's maybe your theta d or qd. This is your theta. Okay, so eventually you want convert to theta d, and there's a steady state error. That's the ESS. It's typically when t goes to infinity, your error theta e t. You have steady state that sometimes or most of the time you don't want that. You also want some good transient performance. For example, this is called overshoot, right? You don't want big overshoot, and you want to convert faster. That typically specified by this settling time. This is settling time, and there's also peak time. This is my peak time, TP. That will be, if you look at the step response, not the error response, that's my TP. Okay, so TP, this is TP, percent overshoot, settling time PS. All the things tells us, kind of specify the desired response you want in the time domain. Okay, okay, let's take a break. Okay, let's continue. So we care about the system response. And for a linear system, the response, it's completely determined by, if you like, the transfer function, like the root poles of the transfer functions. And typically when we consider this, we will study the second order system. And I think everyone should know this. So that's a standard second order system. And here, this kind of a consider that is the damping ratio. This is a typo. And this is natural frequency. There's a few cases. I think just to review, okay, this is less equal to 1. This is called underdamped. And in this case, I have, I think the system response, if my variable system response can be written as the formula for C1, a constant times cosine omega dt plus C2 cosine sine dt omega dt, and times the whole thing times, all right, e to the negative zeta omega n times t. Okay, that's a solution where the omega d is it should be omega n times 1 minus zeta squared. Okay, because zeta is less than 1, so that this can be computed this way. When zeta is critically damped, zeta equal to 1, then we will have a repeated pose. What I mean by pose is the solution to this, the roots of this, right? S1, 2 are the two roots of this equation or characteristic polynomial. This is overdamped case, which is zeta bigger than 1. In this case, S1, 2, you have two real poles. Underdamped, you have two complex poles. This part can two real poles, which is negative zeta omega n plus minus omega n times square root zeta square minus 1. Okay. In this case, the solution is theta e t equal to C1 e to the, I say S1t plus C2 e to the S2t. This case is the same. It's just when there's a complex pose, we can write this way using Euler identity. It's still of this form. In this case, two cases, S1, S2 are both real. So the behavior are mathematically, what do I mean by response? Response is just a solution of the differential equation. And we can write it down second order, we can write it down analytically. So we can use that to describe or analyze system behavior. So that the pose actually determines my overall response. If you think about this, based on this analytical expression, we can actually compute the settling time. Approximately settling time is 4 divided by zeta omega n. And the peak time, T peak, is approximately pi divided by omega n square root 1 over zeta squared. We consider mostly underdamped case. And percent overshoot, PO, it's 100%, e to the zeta pi divided by 1 over zeta squared. So from the expression, actually you can see, you can actually predict the system behavior in terms of the pose, the location of the pose, right? If this is my complex plane, that's my real part, imaginary part. The bigger this guy is, you're further away from the imaginary axis, you're more stable, basically, right? Suppose you're here, that's a negative zeta omega n. That's stable, eventually convert to 0. Okay, and along this line, you know that this part is omega d. Okay, you can see that the larger this one is, if you increase omega d, what happens is that actually this PO is getting bigger, but TP is getting smaller. This guy is omega d. You have a faster response. The initial response reaches the peak very fast. Okay, and but you have a bigger overshoot. That's a trade-off you want to maintain. You don't want this d to be omega d to be too large, then you have too large overshoot. You don't want to be too small, then you have a very sluggish initial response. Okay, so that's a trade-off you need to specify. Okay, Well, that's a very quick, maybe 2-minute summary of the linear controller design in terms of specifying the poles or desired location of the poles. And most of the designs in terms of the second order, I think it's specified with respect to second order control systems. Okay. And we are going to primarily use the state space control design. That's another 2-minute summary of a continuous state space control design, what we should do, right? The first one is that suppose I have a continuous control, linear control system in terms of state space form. And typically, when we talk about control design, we may discuss two types of problems. Mostly we talk about regulation problem. Okay, so that it is kind of problem. Roughly speaking, we want xt convert to 0. When xt convert to 0, what about yt? Liu Ben. du, but anyway, regulation problem, xt convert to 0, y, let's assume that we also want that to be 0. Typically, y is some quantity you want to regulate. You want that to be 0. 0 is some kind of a desired position or location. Okay, but we are more kind of a common problem is tracking, right? Tracking problem. In this case, we can somehow reformulate that as a regulation problem. Most of the time we can do it. So roughly speaking, I will say we can define x tilde t as xd desired t minus xt. Okay, your deviation from your desired state trajectory, and we want x tilde t convert to 0. All I mean is that for majority of problem we care about, the linear control design just try to make sure the state vector convert to 0. The state can be the original state or deviation from your desired state vector. Okay. With this in mind, now let's talk about linear control law. And typically, linear control law is defined as a gain matrix times the state vector, right? So you have a system. This is your control input. This is my state vector, right? And your controller is here, k times negative kx. And maybe you do not only care about the full state, you only care about some kind of a linear function of that state. Okay, so that's a closed loop diagram of a linear control system subject to linear control law. And we can describe the closed loop dynamics, which is x dot equal to, if you analyze the entire closed loop behavior, what you have is ax plus b times negative kx, that's u. And this tells us a minus bk times x. And we call this guy a closed loop. The closed loop system is also a linear system. And by choosing different control gain, k, we can modify the closed loop A matrix. Xunhan, what is the solution of this dynamical system? X dot equal to a closed loop x. What is the solution of this? What? E to the AT times x0, right? This matrix exponential. All right. And if we want to our regulation problem or checking problem, okay, we want the state vector to convert to 0. So we want stability condition, we want, I think we discussed this a little bit, right? We want this guy to convert to 0. So the condition is, so we need the eigenvalues of this A closed loop to belong to the open left half plane. That means real part less than 0, right? So it's here, the domain, this is the imaginary axis, it's here. That's open left half plane in a complex plane. If they satisfy this property and we call this guy, then A closed loop is called pervasive. Or simply stable, or asymptotic stable. I'm just along the way I introduced some terminologies, but that's not essential. All you need to know is that we want to design control gain. And we want to make sure the control gain satisfies the following property for which the closed loop A matrix, all the eigenvalue of this closed loop A matrix lies on the open left half plane. If that can be satisfied, then the closed system will be stable. All the state will eventually converge to 0. For tracking problem, we will just work with the delta or x tilde. That's a deviation from desired state vector. Okay. So because of this relation, the linear control state space design method is just the eigenvalue assignment. It's just find a control gain matrix K such that the eigenvalues of A minus BK equal to eigen desired. That's the so-called eigenvalue assignment or pro-placement problem. You pick some stable eigenvalues that you like, then you design gain, a control gain, so that the closed loop A matrix has desired eigenvalues. That's the typical design procedure. When this problem can be solved, solvability of this problem, which is, so this problem, let's say we can always find such K for all given, that's all for any given eigen desired if A and B pair is controllable. Okay. If not controllable, this problem cannot be, we cannot do this for arbitrary given eigenvalues. So design principle or design procedure becomes the following. You first need to pick what closed loop eigenvalue you need. Then you design K so that closed loop A matrix has the desired or have the desired eigenvalues. And how to choose the desired eigenvalues? Well, see the second order system. Well, we'll say refer to the second order system. You choose desired eigenvalues so that your percent overshoot or rise time match or kind of meet your specifications, and that can be called a dominant pose. And you can place other pose further away from the real imaginary axis, and so that the whole behavior is completely captured by second order system. Okay, so typically that will be specification. Then you choose dominant second order pose pairs, and then you design. Then you come up with the whole overall eigenvalues, and you design K to match or to place the closed loop pose at these desired eigenvalues. Okay. Here, from the specification to here, this is the art. Well, the design is typically it's by engineering kind of experiences. It's typically art, and by try and error, go back and forth. You see that okay, it's not stable. Then you move the eigenvalue further away from the imaginary axis. For example, this axis. If you make it too stable, if you further go here, you put your eigenvalues here, then you may need a really large control action. So nothing comes for free, right? So you try and error to see whether the control action is acceptable or not. So this is art, but can be done, and people have good insight oftentimes. Another way is more about optimal control. I think robotics nowadays use this quite a bit. It's called linear quadratic regulator. And what it does is, let's say, minimize. What I want is the state to convert to 0. So we'll minimize x transpose qx plus u transpose ru d tau, and the subject to x dot equal to ax plus bu, the dynamics. Minimize over all possible control laws. I'm not teaching you this, I'm just mentioning this so that you know the whole picture. All these buzzwords, what kind of role they play in terms of the whole picture. But if you want to know the details, I think you need to read particular part or maybe some books for particular part of this whole framework, okay? So in this way, the solution of this, in this case, LQR is a function, negative K LQR times X. And this K, again, is optimal with minimize this quadratic cost function, right? And this can be computed. There's a lot of packages or MATLAB function. You can be used to compute this LQR again once you give the weighting matrix of state and control. Okay, I just want to mention there's a more classical way to design desired pose and then design the eigenvalue location and design K. Or you can use more kind of a modern control theory or more optimal control that you can design again in terms of LQR solution. Either way is fine. It's a linear control, it's a done deal. It can be easily defined, accomplished. Okay, I gave you somehow 10-minute summary of the control design for linear system, and that's all you need to know to really understand the motion control for robotic systems. Any questions so far? Again, I'm not teaching you this, I'm just mentioning some of this in case you have learned. I assume most of you have learned everything I talk about today. You may forget, but that's fine. I'm telling you each of these terms is what their meaning, and all we need is that here, okay? All you need to know is that you can design a linear feedback gain matrix so that you can place the closed loop eigenvalue to make sure the closed loop system is stable. And stable means trajectory of state vector convert to 0. If you don't want them to be 0, you want to be 2, then you just make sure the error vector convert to 0. So no matter what, let's assume we want something or the state vector convert to 0. Okay, that's all we need to know so far. Okay. Now let's get to the actual design of the motion control part. Okay. As I mentioned, there's different categories depending on whether you are controlling things in terms of, whether the reference is given in terms of joint, in the joint space, or in the task space. Okay. Let's look at them one by one. And first of all, let's talk about so-called velocity resolved control. What we mean by that is I have a robot. Let's draw it here. Let's say robot. For my motion control designer, for us, all we need to send to the robot, suppose, is the velocity. Let's first talk about joint case, okay? Let's say all we need to talk is U. In this case, is Q dot. These are Q dot. Okay, and the robot will move, and the output is Q. In this case, each joint, Qi, can be directly controlled in the sense that the velocity can be directly controlled. If we want to write down the dynamics of this system, the dynamics is Q dot equal to U, which is in Rn. In other words, Qi dot equal to Ui. It's almost like a what? A trivial system which is a single integrator. You can directly specify the velocity of the joints. Whether that's a good assumption or not is another story. Let's assume that's what we need to tell the robot. If this bothers you, you should think about this. Okay, this is what I send to the robot, but the inside robot, there's some kind of internal controller will determine there's some internal controller we don't care about or we don't have any control over, right? And tell the robot the current is joined. The current, this is the physical plant of the robot. The actual robot plant then moves, okay? But we don't need to worry about that. Let's assume that this is joint velocity is all we need to do. Okay. Here is what we want to do is motion controller. And what we're given is QD, a reference. This is a reference from a motion planner, okay? This is reference from motion planner. So this system is really simple. And if you look at this part, if you look at the input-output behavior, let's just look at this system. I know there's a lot of things going on inside, but I don't care, right? If you look at input-output behavior, what does this mean? This is a linear system, which is, I just wrote down before, this is Q dot equal to U. Can you control this? It's a linear control design problem we just reviewed, right? How should we do it? Eigenvalue assignment problem, that's it. So let's look at how we do it. The joint space dynamics is a single integrator, which is in Rn, right? I'm talking about vector now. And joint space tracking problem becomes standard linear tracking problems. Okay. In this case, we define, as I mentioned before, you would design the error as your state. Okay, in this case, my error is I call the Q tilde, which is QD minus Q. Okay, and if I do this and say Q tilde is this, then I can, as a position error, if I plug in this control law, this is a linear control law. What is given? QD is given, and QD dot is also known. This is my error or state vector. What I want is I want Q tilde to be 0, right? That's what we want. And so if I plug in, I can derive this, but this is really simple. Let's say Q dot equal to what? U. And I specify my U to be desired Q dot plus a correction, a feedback correction term. K, let's call it K0 times Q tilde, the error. So this is my control, right? That's my control. That's from here, right? This is my control law. This is a feed forward term. This is a feedback term. If you don't have feedback term, then you have to be, everything has to be perfect. If you have feedback term, that's more robust. Okay. If you plug in this to the system dynamics, this is already plugged in. Okay. So if I derive it, if we move things to the, let's say move this guy to the right, then what we have is QD dot minus Q dot plus K0 Q tilde equal to 0. That's a vector 0. All right. What about this term? This is Q tilde dot. Okay. So what we have is Q tilde dot plus K0 Q tilde equal to 0. Or if you want to see more explicitly, this Q tilde dot equal to negative Q0 Q tilde. What's the solution of this, Yinghan? E to the negative K0 times T times Q tilde initial position, right? Initial error. What we want is Q tilde converge to 0, stabilization. What kind of K can achieve that? All I need to make sure is we only need to ensure the eigenvalue of negative K0 belong to open left half plane, as we just mentioned. Make sense? What's the dimension? What's the dimension of this K0? It's an n by n matrix, right? It's a game matrix, and oftentimes the aerodynamics is stable if negative K0 is a Hurwitz. The eigenvalue of it is on the open left half plane. So a typical, I would say, common choice is a K0. It's a matrix, right? It's n by n that can specify n squared numbers. But typically we'll just say K01, K02, all the way K0n. All the other part is 0, where K0I is bigger than 0. You just have a diagonal matrix. Each term of it is its element on the diagonals is non-negative or it's bigger than 0. Then the negative of it is smaller than 0. I will make sure everything is Hurwitz. You just need to choose this gain. This is almost like a damping. Under this design, we can ensure Q converts to QD or Q tilde convert to 0. Okay, that's simple, right? I assume that you feel bored about this. This is really simple, but I want to tell you all the rest, more complex cases are equivalent to this case. Not mathematical equivalent, idea-wise are the same.